Should we get started? Okay. Hey guys, thanks for attending this talk. This talk is about fast distributed online classification. And this is joint work with Ram Sriharsha, who recently joined Databricks as the product manager for Apache Spark. And I am Prasad Chalasani. I'm the SVP of Data Science at MediaMath, which is an advertising technology company that builds a real-time bidding platform to help manage, run, and execute and optimize ad campaigns. So here's the high-level summary of what this talk is about today. We leveraged recent research in theoretical and empirical machine learning to build a fast, highly scalable, online, distributed, and single-pass machine learning package. Okay, and this has several useful features that are not simultaneously present in any other machine learning package in this category. And we did this in Scala on top of Apache Spark. Okay, so that's so in fact, there's a lot of terminology there in what I just said, but I hope to make all of those things clear to you by the end of the talk. Okay, so here are your key conceptual takeaways for that you can hope to get by the end of this talk. Okay, one is we'll put supervised machine learning in a mathematical framework, which is probably familiar to most of you. But more importantly, you will learn about the distinction between online and batch learning, and learn about how online learning can be very useful and important, and what are some of the advantages of online learning compared to batch learning. And then you learn about some of the challenges in designing online learning systems and how those challenges can be overcome. And finally, you learn about how an online learning system can be implemented in a parallel and distributed setting on top of Apache Spark. So let's dive in. So supervised machine learning is a setting that's probably familiar to most of you, but nevertheless, let me recap. Basically, in this setting, we are given a training data set, which is a collection of labeled examples. And then the goal of this is to fit a predictive model to this training data set that we can use to make predictions on the test data set, which is the unseen observations, unseen data. Okay, so let's put this in some mathematical notation. So what we have here is a training data set, D, that consists of n labeled examples. Each labeled example is a pair xi, yi, where xi is a k-dimensional sort of a k-dimensional vector, which represents the features in the observation, and yi is the label. And the label is typically, you can think of that as just a 0, 1 label in this case. For example, if you have an advertising situation where, okay, so the xi features, the feature vector could represent the features associated with the ad impression, for example. And the yi label can represent whether or not someone clicked, the exposed user clicked on an ad. Okay. And also we're given in this framework, we're given an error metric or a loss metric. Okay. So when I say a loss metric, I mean when a certain prediction P is made, go ahead.
Features are numbers, right?
Yes. In the representation, there are numbers originally. I mean, eventually. In the beginning, they may not be numbers. Okay. Okay. So by the way, I'm glad you're interrupting me. So please feel free to stop me if I'm going a little bit too fast in some areas. Okay. So when you make a prediction P and the real label is Y, we define what's called a loss metric, L as a function of P and Y. So that tells you what is the error of making a prediction P when the true label is Y. And we are also given a family of functions among which we want to find the model. Okay? So typically, it will be a family of functions that is parameterized by a weight vector W. So fw of x is the model that we're trying to find. And the goal of supervised machine learning is to find the vector, weight vector w, that minimizes the total loss over all the over the entire training data set. Or the same thing, which is minimize the average loss. These are the same thing, minimizing, because they just differ by a factor of n. So this is all a very abstract definition. Let's see how this becomes concrete in the context of logistic regression. So in logistic regression, the underlying model, prediction model, is simply the logistic function of the dot product of the weight vector and the feature vector. So here, the w is the weight vector, and x is the feature vector. Both have the same dimension. And you do w dot x, and you do, you take the negative of that and raise e to the minus w dot x, and then pass it through this logistic function. And this function has the nice property that the value is always some continuous number between 0 and 1. So you can interpret that as a probability. And then I said there should be a loss function that we need to define, right? So we can define the loss function in many different ways, but in logistic regression, this is a common loss function, common way to define loss, which is called the log loss. And you'll see that it has the right properties, right? So just to refresh notation here, xi is the index I refers to the ith example or the ith observation. So xi itself is a k-dimensional feature vector, okay? And w is the k-dimensional weight vector. So why are we defining the loss this way? It makes sense because let's say you look at the possible values of the label yi. Those could be 0 or 1, right? So let's say you take yi equals 0. Then the first term vanishes, and you're left with the loss function liw is just minus log of 1 minus the prediction, right? So if the prediction is smaller, this loss function will be smaller, right? So this makes sense. So similarly, you can look at the case of yi equals 1 and understand that liw is a reasonable way to define the error that you're making when you're using the weight vector w to make a prediction on the ith example, okay? And the overall loss over the entire training data set is the sum of these losses over these individual training examples, okay? That's the total loss, LW. And our goal is to minimize LW. So let me actually, before moving on, let me pause here and say that, so if you see here, the goal is to minimize LW, right? So it's essentially, machine learning is essentially an optimization problem, right? You can see that right away. And this loss function that I defined this way has a nice property that it's convex. And what that means is there is a single global optimum. There are no local minima. And you can use iterative methods to arrive at the optimal W. So let's see how that works in a simple, very simple example where there's just one feature, and therefore there's just one weight, W, to learn. And when I say the loss function is convex, it essentially, roughly speaking, it means that the loss function has the shape of a bowl in general. In this case of W being one-dimensional, the loss is just a parabolic, not parabolic necessarily, but a sort of a two-dimensional bowl or one-dimensional bowl, if you will. But the main point to notice here is that there is a single optimum value of W, where the loss function LW is minimized. So let's see how we'll find this minimum or the best W iteratively. Okay, let's say we start at W equals 6, somewhere on the right-hand side over there. And then the first thing you do is you have your current guess or current value of W that you found so far. You look at the gradient of the loss function at W. Okay, the gradient here is, let's say, the gradient here, the definition of the gradient is just the first derivative of the loss function with respect to W. And here, let's say the gradient delta is 1.2. So what you notice here is the gradient is positive. Positive means that when you increase W, you're going to increase the loss. So to reduce the loss, you need to move in the direction opposite of the gradient, right? So that's why we do an update, where we update W to a new value W prime, which is W minus lambda times the gradient, where lambda is a positive number. So we're moving in a direction opposite to the gradient, Okay. So the basic idea is in gradient descent for optimization is you start with an initial guess of the weight vector that you're trying to optimize. And then at each iteration, you compute the gradient of the loss function with respect to this weight vector. Okay? And let that gradient be gt. And the update step is simple. It's just w prime is equal to w minus lambda times gt. And like I said, gt is the vector gradient. In the case of multidimensional w, it will have a vector form. Okay? And lambda is the learning rate. So to help with intuition on this, think of the gradient as giving you the direction in which you want to make the update, right? And the learning rate, lambda, is the size of the update. Okay, so it's the step size, roughly speaking. Any questions so far? Okay, cool. So let's review the gradient again, right? So the gradient is, like I said, is the derivative of the loss function with respect to w. And so L is the total loss. Remember, it's the sum of the losses over all the examples. So you can write the gradient as the sum of the individual gradients over the individual examples, right? So GT is the sum of the GTI. So just keep that in mind. It's going to be useful later on. So so this is called, the way the method I just described is called batch gradient descent, because what you do is you have to compute, to make one weight update, you have to compute this gradient with respect to the entire training data set, okay, to make one update. And we repeat this iteratively until we converge to the optimum. So as you notice, as you may have noticed, this is not highly scalable, right? BGD is not very scalable to large data sets. Okay? So, is there a way to resolve this? So there is, it turns out, and that's called online gradient descent or stochastic gradient descent. The idea of that is to do a drastic simplification of batch gradient descent. Remember, instead of doing a gradient based on the entire training data set, where you sum of all these gradients, and then doing this w minus lambda gt update, we just take one of the gradients of one of the examples. But we should make sure that we are seeing these examples in a shuffled order, right? So intuitively, you can imagine if you look at just all positive examples first, all 1 labels first, and then all 0 labels, that's going to be really bad for online gradient descent. Okay, so the idea is to shuffle the data if it's not already naturally shuffled. Very often in many applications, your data is already shuffled. No one, it's very rare to see examples where you only see positives first and then all the negatives. So the shuffling is not actually a big deal, okay? So this drastic simplification works extremely well in practice, which is not very intuitive, right? But okay, so let's contrast again batch versus online gradient descent. So batch is to make one step, like I said, you have to compute the gradient with respect to the entire data set. So each update is extremely slow, okay? But each update goes in the right direction because the gradient is exactly the right gradient, right? By contrast, online gradient descent, each update is extremely fast. You compute the gradient with respect to one example, and then, but the thing is, you may not necessarily go in the right direction because you're computing the gradient with respect to just one example, which may not exactly be the right gradient always, right? So there is this sort of trade-off, but in practice, like I said, online or stochastic gradient descent works extremely well. And the reason it's called stochastic gradient descent is because of this thing that I just mentioned, which is the direction of the update is not always necessarily in the right direction. So if you look at this picture turned out bad, but okay. So if you look at visually how we converge to the optimum in these two kinds of algorithms, batch versus stochastic gradient descent, you'll see what I mean, okay? So what I'm showing here is a two-dimensional weight vector. And the paths here that you see, like in red, are the paths of the search for the optimal W. Okay, so you're starting at the outer. So in a two-dimensional space, a convex function is just like a bowl, right? It's like literally a bowl, and the optimum is at the center of the bowl, the optimal W. So the idea is to start at some W and somehow reach the bottom of the bowl. Okay? So the top picture is batch gradient descent. So every update is going in the right direction. But as I said, each update is very, very slow. Okay? The bottom picture is stochastic gradient descent. So it kind of zigzags and makes its way to the optimal point. So that's just to get a rough intuition of these two algorithms. Okay. So that was batch versus online gradient descent. We can generalize that to batch versus online learning. Okay? And it's the same distinction applies here. So in batch learning, we process a large data set and come up with a model, and then use that model to make predictions on the test data set. And so this has the drawbacks that I mentioned, similar to gradient descent, batch gradient descent, which is that it's very impractically slow to make an individual step. Okay? And then the other thing is that as more data becomes available, there is no notion of incrementally updating a model. You have to do this entire batch process all over again to update your model. On the other hand, for an online learning, for each training example, we generate a prediction, we compare with the true label, and then update the model based on what we see. Okay? Update the model weights. And then for each sort of test example, we predict with the latest learned model. Okay? And so there are lots of benefits of online learning, which I want to highlight here. So online learning does not pre-process the entire training data set, right? So it's very suitable for situations where data is streaming in. But I will have more to say about that later on. Okay? And it does not explicitly retain previously seen examples, so it's very space efficient. Okay? And it's very lightweight, very space and time efficient updates. And there is no sort of distinct training and testing phase, right, as opposed to batch learning. So this is a continual learning situation, right? The learning is happening continually as each example is processed. The model is incrementally improving. And so you can imagine how it's easy for an online learning algorithm to update or to adapt to changing patterns. And so this is what I mentioned before, is when you have new data, you can easily update the model instead of having to go through a laborious retraining phase. And this is the last property is very sort of counterintuitive, but it makes online learning algorithms have much better generalization than batch algorithms. So this is the online learning paradigm. Okay, so just to recap. So as each example is seen, you make a prediction and then update your weight vector model. Okay, so let's look at what kind of situations online learning can be useful. Okay, so you might think that online learning is only useful in situations where data is streaming continuously from some source, but that's not necessarily the case. Even in a batch situation where you have an extremely large data set, okay, but just batch training is very, very slow. Even in a large data set where, even though it's not a streaming data source, it's just some offline data that you want to fit a model to, that training can be very slow if you do just batch training. So in that setting, online learning can be very useful. And also, let's say there's a restriction that you can only make one pass on the data. Okay? So even there, online learning is highly suitable because it just streams through it just processes one example at a time and updates the model. And so, of course, the other situation where online learning is useful is when data is arriving in real time and your model needs to update quickly and adapt quickly to changing conditions, and you need to make predictions fast. Okay? So online learning is very useful in many settings. And so let's look at a couple of concrete examples where this online learning is actually useful. So here, the first example is in the advertising area. For example, the company where I work, MediaMath, we build a real-time bidding platform that helps advertisers manage and run their campaigns. So what the real-time platform does is it listens to hundreds of billions of ad opportunities coming in from the ad exchanges. And then in response to each opportunity, it has to, the platform needs to decide, it needs to make a prediction of the probability that a user exposed to the ad, what's their probability of conversion, of buying something, okay? So that's a typical sort of a learning problem for a real-time bidding platform. And so this prediction has to be made as a function of several features. For example, like hour of the day, browser type, region, age, and so on. Okay? So online learning here has clear benefits, right? Because the models are updated very fast to reflect the latest observations. So you never have a stale model because your model always reflects what it has seen until now, right? And then these lightweight models are extremely fast to train and compute in real time. So the other class of applications is in the Internet of Things domain, where vast amounts of data are actually streaming in from sensors or devices. And the models need to adapt and respond quickly, right? So for example, Nest thermostats. They can use behavioral data to make predictions of the preferred room temperature, okay? Or self-driving cars can use sensors and information from other cars to predict a collision. And similarly, in the clinical area, we can use sensor information of vitals or physical activity to predict a cardiac event. And finally, in smart cities, we can use sensor information to predict traffic congestion. Okay. So online learning is very useful. I hope that is sort of more or less clear. But there are many challenges in designing an online algorithm, online machine learning system. Okay. And so in this talk, we'll talk about 4 different challenges. The first one is what is called the feature scales problem, right? So here's an example. So let's say in the wearable devices domain, there are 2 different features. One is the heart rate, and the other is step count. The heart rate can go up to like 200 maybe, right? And the step count is can go all the way to, who knows, right, 500,000 maybe. This is probably the daily step count. So these 2 features are at very different scales, right? So when in that kind of situation, convergence can be very slow in an online algorithm. I'm not going to go into the details, but when scales are very different across features, the rate of convergence to the optimal weight vector is very slow. Okay? So to remedy that, you might imagine that you could normalize each feature, right, divided by the maximum possible value that feature can have, right? But you cannot make a pass on the data to figure out the maximum possible value of the feature. You cannot make a separate pass on the data, right? You have to respond in real time. So the range of features is not known in advance, right? So what do we do in this situation, right? So what we need is a single pass algorithm that does this normalization in an adaptive way. So it makes a guess of what is the maximum possible value and keep updating it, and then compensate it and make a compensating update on the weights in such a way that the result is almost as if you knew the entire data set, you knew the possible range of values. Okay? But again, I'm going to skip these details. This was an algorithm that was proposed a while ago, and we implemented this in our machine learning system. Okay, so the next challenge, I'm going to pause here if there's any questions. Okay. All right, so the next challenge is when features have very different frequencies, when sparse features have very different frequencies. So here's what I mean by that. So some features can occur, some sparse features can occur much more often than other sparse features. So for example, let's say take a feature country. Country has 200 possible values, and it's possible that some values can occur much more frequently than others. Like right? Or similarly, an indicator feature that indicates whether a user has visited a particular site can happen much more frequently than whether a user has purchased something, okay? So these are very different frequencies. So what's the problem with that? The problem with that is, so I mean, very often rare features are highly predictive. Features that are occurring in almost every example are probably not very predictive, right? So if you use the same learning rate, okay, for all these features, there's going to be a problem, and the problem is slow convergence again. So roughly speaking, what happens is, remember the learning rate is the step size in the updates, right? So if you have the same step size for frequent features as for rare features, the weights of the rare features will make very slow progress towards their optimal values, right? Because they don't get updated that often, and the step size is the same as the step size of a frequent feature. So the rough idea is that rare features should have a bigger step size. So the feature step size needs to be adaptively determined based on the frequency of the feature. Okay? So in other words, you want to, roughly speaking, you want to pay more attention when you see a rare feature. So certainly there's a lot of examples where that feature has not occurred, and suddenly you find an example where that feature is on, and then you have to give it a bigger, you have to take a bigger step when you update the weight corresponding to that feature. So this type of algorithm, there's an algorithm called ADAGRAD that was proposed a while ago, which stands for adaptive gradient, and this is also implemented in our system. Okay, the third challenge is how do we encode sparse features? So we all know what sparse features mean, right? So let's say there's a feature called site domain. So there's plenty of possible values of site domain. We don't know what they are, what are the possible values in advance. And let's say there are different possible site domain values, and typically, conceptually, we want to encode these site features as one-hot vectors. Like google.com might be like 1 and the rest is 0, right? Each position in this vector stands for a different site domain. Yahoo might be 0, 1, and so on, right? But we don't know all possible values in advance. And we cannot pre-process the data again, like I said. We cannot make another pass to figure out all these possible values, all right? And then the other thing is we don't want to store these sparse vectors explicitly. We don't want to have a long vector of length like a million, with million possible sites, and have all of them be 0 except for 1. All the entries be 0 except for 1, right? So we don't want to do, we have all these constraints. So there is a nice elegant trick to solve this called the hashing trick, which we implemented. So this is how this trick works. So let's say we have an observation where the country is China and the age is 32 and the domain is google.com. The first thing we do is we hash the feature names. We take country underscore China as a string and hash it to some number. And age is a name of a feature, we hash that. And similarly for the domain. So we get these 3 hash values. And then we represent this observation as a map, as a special kind of a map, where in the case of the categorical variables, we map it to 1. And in the case of the age, which is the middle one, we actually map it to the actual number. So back to your earlier question is eventually all the features are numbers, right? All the feature values. So this trick works extremely well in practice, despite the fact that there can be collisions when you're doing a hash function. But I'm not going to go into that. So the nice thing here, as I said, is there's no explicit representation of long vectors because it's a sparse representation. And there's no need to make a separate pass on the data, right? So, sorry. Any questions so far?
Yes, please. One.
Yeah.
About the figure 1.0, the third element that set.
Yes.
The first one I understand, the second one also, but what's the...
Oh, third one is also just like the first one, like it's the domain.
But why do you map that to 1?
Because the domain is a categorical feature and its value is Google, right? So all it indicates is that the occurrence of domain equals google.com. So it's just like the first one.
But you could do the same as age, no? You could just do age_32.
You could do that, yes, in case if you want to treat it as a categorical variable. But age being a continuous number, it's better to, it depends on what you want to do.
Because you have more information, right?
Yeah, you have more information, exactly. Yeah.
Are you addressing the problem of non-linearity? Because you may have a positive correlation
Yeah.
of medium age and click-through,
Yeah.
but you may have something negative for both low and high age.
You could, yeah.
And then
Then you could bin the age into 3 different bins, maybe, and then you can represent it that way.
But this is not part of the algorithm. So
No, this is not part of it.
Okay.
Yeah.
How do you fit the training and predicting step once you have built the sparse vector with different hashes?
How do we fit the model?
This is not normal vector. This is a vector that has a different size each time. So how do you use it?
Okay, so this is a special implementation of a map. It's a hashed map implementation that we just use the package from Google. Conceptually it's a map, really. Okay, it's with a varying number of entries. Think of it as a huge bit vector, in fact. Okay, it's a bit vector, and you're saying that a bit in a certain position is a very long bit vector, and effectively you're saying a bit in a certain position is turned on.
Sure, but typically you have a fixed size vector in machine learning, and you have a variable size vector. I think that's what we would.
Oh, I see what you mean. Yes, so this is not actually represented explicitly as a vector. Think of it just as a very fast map. That's all it is. Okay, and we do all the weight updates not by treating them as a vector, but we look at the map. Okay, so conceptually it's just a hash map. Cool. Okay, so the last challenge I'm going to talk about is how do we implement an online learning system in a parallel distributed setting? Okay, and this is very important because most of the big data that we see live either in HDFS, in a Hadoop cluster, or in S3 buckets on an AWS cluster. So it's very important for the machine learning system to be able to work directly with that kind of data, and also at the same time leverage the parallelism that the AWS cluster or Hadoop cluster offers. So we implemented this in Scala on top of Apache Spark, which is fast becoming the most popular big data platform out there. And so roughly speaking, that implementation works like this. So we randomly repartition the data into shards or subsets of the data, and then apply stochastic gradient descent to fit a model to each shard of the data, okay, which is inherently a sequential process. But then we aggregate these separate models that we built for each shard in a tree-like fashion. It's something called tree reduce, which I will not go into, but it's a very fast aggregation. And then, so the side benefit of this is that it leverages the parallelism and fault tolerance that you get from the underlying Hadoop or Spark cluster. Right. So all throughout this talk, I've been talking about a machine learning system that we implemented, which incorporate techniques from recent research. So this system, we call this slider. Slider is apparently a fast pitch in baseball. And we plan to open source this soon. And this is a fast distributed online learning system with several useful properties that are all listed there, which I will not go into, but I think we touched on most of these. So this is written on Spark, on top of Spark. And one of the things I didn't talk about is this is usable as a library in other JVM systems, which is also pretty important if you're working in that sort of ecosystem. And so I'm going to contrast Slider with a couple of other existing machine learning frameworks that are very popular out there. One is Warple-Wabbit, which is a C++ based system that incorporates many of the tricks that I talked about here, but it's not implemented in Spark, and it's not implemented in a JVM language, right? And therefore does not leverage the fault tolerance and parallelism that you get from a Spark type of system. And the other one is a Spark ML, which is the machine learning package that comes with Spark, packaged with Spark as part of the distribution. So as you can imagine, several of the techniques are, several of these features are present in each of these separate learning systems, but neither of them has all of the features that we have. Okay. So I want to quickly go through a very simple code example to show how simple it is to use Slider. So this is only for people who are sort of familiar with working with Spark. So the first line here loads the data frame, loads the data set, which is impressions data in the case of ads, and then makes a training and a test data frame based on the dates. And the next step is to specify a feature specification. We're specifying there are 4 features. There's a country, which is categorical, there's age is numeric, site domain categorical, and so on. Okay, and then we use that feature specification to create these encoded, using the hashing trick, we encode these into RDDs, okay, using that function, sparse instances. So this, now we have 2 different RDD, we have a training RDD and a testing RDD. And then we specify a machine learning configuration. We say we want to run the SGD model, SGD algorithm, stochastic gradient descent. And then we build a model equals RDD.train. That actually trains the model on that training data set. And then we use that to compute scores on the test data set. And so the output of computing scores is just, you get an RDD of tuples. Each tuple has the actual label and the predicted value. And then from there, we compute the AUC, which is a metric for the accuracy of a machine learning system. So we did a very simple informal comparison between Slider and Spark ML. And it looks sort of like this. We took the advertising example. The task is to predict conversion probability from ad impression features. Okay? So there are 14 million impressions and for just one campaign over, I think, about 25 days. And there are 17 categorical features and 2 numerical features. And we trained on the first 80% and tested on the remaining 20%. And with Spark ML, this is what we did. We used the pipeline framework in Spark ML, for those who are familiar with that. This makes 17 passes over the data because there are 17 categorical features. And for the various reasons I mentioned, if you're not doing an online algorithm, you have to make passes over the data to figure out what are the possible values and so on. And then the whole scoring and training time is about 40 minutes. And the AUC is also not great. By contrast, in Slider, we make one pass, we train it in 5 minutes, and the AUC is much better with no tuning at all. So, I mean, to be fair, I think with proper tuning, this could do much better, but we didn't have to do any tuning. All right, so I just want to leave that there for a while, and then go ahead, yeah. No, we did not do that. That's work in progress, and that's what I was going to mention now. There's other work that I didn't have time to talk about, which is we worked on an online version of k-means clustering, and also another different online learning algorithm called FTRL. We also implemented that. And ongoing work is, like you just mentioned, is benchmarking properly with other machine learning systems, and also building something on top of Spark streaming. Thank you.